Welcome to this particular class. In the last class what we have seen silicon dioxide, and in this class let us see photolithography. So, for photolithography the name comes from a Greek word where if you divide it is like a carving of a single stone, alright. Now photo stands for photon or light, right. So, we use UV light for performing or creating a pattern onto silicon substrate. So, let us understand how photolithography works, and we will take one example to understand the different steps involved in lithography. So, in photolithography, if I write down photolithography, as you can see here, photolitho and graphy, right. You use photoresist, these photoresist are two types, positive photoresist and negative photoresist. Then you use masks. Masks are two types, bright field mask and dark field mask. Bright field mask and dark field mask. Okay. Now, photoresist positive and negative, mask bright field and dark field. This was easy. Now, the step for performing lithography is you take a silicon wafer. We will take an example of a silicon wafer. Okay. Take a silicon wafer. You clean the silicon wafer with RCA1 and RCA2 cleaning steps. Then you spin coat photoresist, spin coat photoresist. So, let us say this is our photoresist, alright. It can be positive photoresist, can be negative photoresist, spin coat photoresist. Next step is you soft bake. You bake this photoresist at 90 degree centigrade for 1 minute on hot plate. Next step is you load the mask. Load mask. This can be bright field mask or a dark field mask. Now, what is bright field mask? What is dark field mask? I will tell you. In the next class, I will show it to you also. Here, I will draw the bright field mask and I will draw a dark field mask. Where my field is bright and the pattern is dark, field is bright and pattern is dark is called bright field mask. Alright, you can see here the field is bright and my pattern is dark. This is field and this is the pattern, right. In dark field mask, my field is dark. Okay, you assume that everything is dark, okay, just completely where light cannot pass through it, like this, complete dark. So, when my field is dark and pattern is bright, you can see the pattern is transparent, right. This is called my dark field mask. Field is dark and pattern is bright, dark field mask. When field is bright and pattern is dark, then we have a field is bright and pattern is dark, we have a bright field mask. So, in this case everywhere whatever I am drawing here with red shade, right, is chrome. alright. We are talking about chrome mask. So, mask is made up of different material, right. One is called chrome mask, another one is called Fe2O3 mask, alright, chrome mask and Fe2O3 mask. So, this all red color thing is actually a chrome, you assume that it is a chrome. What will happen, what is the reason of using dark field mask and bright field mask at certain point of time, I will tell you, but right now you understand that the light cannot penetrate to metal, is not it? It is very simple, light cannot pass through metal, right. So, wherever this red color is there, light cannot pass through it, where there is a transparent area, light can pass through it, right. In this case you can see very clearly here that the light cannot pass through this metal, but light will be able to pass through this area, is not it. Here the light will be able to pass through this area, light can pass through, wherein through this area it is not able to pass through. So, for this region it is not able to pass through, where transparent region is there, it is able to pass through. So, the first one is our bright field mask, one bright field already is written mask. The second one, which is this one, is the dark field mask. Okay. So, this is the difference, bright field mask and a dark field mask. Now, I told you that these are a chrome mask, chrome mask. So, we have taken a silicon wafer, RCA1, RCA2 cleaning, then we have spin coated photoresist, and we have a soft bake at 90 degree centigrade 1 minute on hot plate, then we load the mask. After loading the mask, we expose the wafer with UV light, ultraviolet light, expose the wafer with UV light. Now, you will see the difference. Okay. So, now assume that we have used this bright field mask. So, this mask is bright field, alright, and the photoresist that we have used is positive photoresist, bright field mask and positive photoresist. So, then after soft bake you have to load the mask, expose the wafer. The next step is develop the wafer, in photoresist developer. You go back. Once you expose the wafer with UV light, you unload the mask and dip the wafer in a photoresist developer. After that, the next step is hard bake. (120) 1 minute hot plate, 120 1 minute hot plate, hard bake, and the process is over. All right. So, these are the steps. Now, let us understand the same example. What will happen if I use this bright field mask with positive photoresist and negative photoresist. Okay. Bright field mask with positive photoresist and negative photoresist. So, in one case I have positive photoresist, in second case I have negative photoresist. This is the top view. This is a cross sectional view, right. So, in one case what I said, there is a positive photoresist, in second case I have a negative photoresist, alright. This is my positive photoresist, this is negative photoresist. Now, so I have everywhere positive photoresist, here I have everywhere negative photoresist, positive, negative, alright. Now, what is the next step? If I have positive photoresist, if I spin coat positive photoresist onto this silicon substrate, the next step is I have to go for the soft bake, right, soft bake. After soft bake, I will load this mask onto this particular wafer, right. I will load this mask onto this wafer. That means, let me show on the cross section. I will load the mask, I will load the mask here, and I will load the mask here. So, cross section of this would look like the one that I am drawing here. What is this mask that we are using? We are using bright field mask and we are using positive photoresist. In this case, we are using bright film mask, but negative photoresist. Okay, positive, negative. Now, I will expose this wafer through the mask with UV light. Same thing goes for here also, UV light, alright, and then I will develop the wafer, develop in photoresist developer. This also I will do the same thing, develop the wafer in photoresist developer. In this case it is a positive photoresist developer, in this case it is a negative photoresist developer. When I do that and I unload the mask, when first of course we have to unload the mask and develop the photoresist, right. So, the step is spin coat the positive photoresist onto the substrate, then soft bake, then load the mask, then expose the wafer through the mask with UV light, then unload the mask, next develop the photoresist. What will happen is that for the positive photoresist the unexposed region would be stronger. Which is unexposed region? This region where there is a pattern is an unexposed region, right. So, in positive photoresist after you develop here, what you will get is, that this region you will see that photoresist is still there. You see here this one, in this case the unexposed region, which is this region, right, is stronger, and you can see that is why you can retain the photoresist after developing into positive photoresist developer. While in case of negative photoresist, the unexposed region becomes weaker, the unexposed region, which is this region, becomes weaker. So, what you will have is opposite of positive photoresist, like this, right. How the mask was looking? Mask was, this was a mask, right, cross section of bright field mask. So, what you see here is the pattern that you had on the bright field mask, same pattern has been retained in case of positive photoresist, while the complementary pattern came on the negative photoresist, opposite, right, where the area was protected, this is area is etched, where the area was protected, same area is protected in the case of positive photoresist. That means that the positive photoresist you can pattern the same pattern that you have on the mask, you can replicate the same pattern using positive photoresist onto the wafer. In negative photoresist, the opposite of the pattern that is there on the wafer will come. That means that the area which was dark in this case of mask, that area will get etched, the area which was bright will be there. In another way you can say that the unexposed region, okay, let me write down in this one, it is becoming easier, it will become easier for you. Positive photoresist, negative photoresist, the unexposed region, in case of positive photoresist will become stronger, in case of negative photoresist will become weaker, right. Exposed region, in case of positive photoresist will become weaker, in case of negative photoresist will become stronger, right. That is, you can see here the region which is unexposed in case of positive photoresist is becoming stronger, the region which is unexposed in case of negative photoresist is becoming weaker, right. So, the unexposed region is stronger in positive photoresist, unexposed region in negative photoresist is weaker. If you say about exposed region, the exposed region in positive photoresist is weaker, while the exposed region in the negative photoresist is stronger. Alright. So, you now learned how to grow a silicon dioxide on a silicon wafer, right. You know how to grow a silicon dioxide on silicon wafer, everyone? Yes, because we have seen thermal oxidation technique, right, SiO2. Okay, I am just growing silicon dioxide on one side of the wafer. Okay. Now, what I want is my silicon dioxide, I want to create a step. You have seen the step earlier that we used to understand the thickness of silicon dioxide, right. This step I want to create, that means that in this region silicon dioxide is etched, right, it is etched. this region, is not it. So, what I will do is to get this particular pattern, I will start with a silicon wafer, grow silicon dioxide, right. The next step is I will spin coat positive photoresist, alright. I will spin coat positive photoresist. After coating positive photoresist, I will soft bake 90° 1 minute hot plate. After doing that, we will load the mask. So, let me do it here. You have oxide, you have photoresist, okay. Load the mask, alright. I load the mask that has pattern like this. Okay. Alright. Now, this is my bright field mask. After that, you have to expose this wafer using UV light. After exposing, you have to unload the mask, right. Unload the mask. After exposing, unload mask and develop the photoresist. If I do that, what will I have is silicon wafer, my oxide and photoresist will stay in the region which is not exposed to UV light, right. The unexposed region will get stronger in case of positive photoresist. You can see the unexposed region is stronger in case of positive photoresist. The next step is I will dip this wafer in BHF. BHF is okay, but before that I have to perform post bake, right. After this I have to perform post bake. Post bake is done at 120° centigrade 1 minute on hot plate, alright. So, if you repeat, it is positive photoresist spin coating, soft bake at 90° 1 minute hot plate, load the mask, expose the wafer, unload the mask, develop the wafer, develop the photoresist, then post bake 120° 1 minute hot plate, then you dip this wafer in BHF. BHF will etch silicon dioxide from the area which is not protected by the photoresist, right, which is not protected by photoresist. So, if I draw it after this particular work, right. If I go to the next slide, how it will look like. If I dip that wafer, which wafer? Let me draw it again here. The wafer where your positive photoresist was protected in this region, and from remaining region positive photoresist was developed. This is your positive photoresist, this is your silicon dioxide, this is silicon. Now, I dip this wafer in BHF, buffer hydrofluoric acid, then what will I have? If I dip this wafer in BHF, what will I have? I will have this is positive photoresist, silicon dioxide, silicon, right. You can see that silicon dioxide from this region got etched, but the silicon dioxide that was protected by positive photoresist is intact. After this, the next step is if I dip this wafer in acetone. Acetone is stripping agent for positive and negative photoresist. For positive and negative photoresist, acetone is a stripping agent. So, if I dip this wafer in acetone, what will I have? I will have silicon silicon dioxide. This is what I want, right, this is what I want. Let us go back. You see here silicon and silicon dioxide, same thing I got here, silicon and silicon dioxide, is not it. This process is called photolithography. So, if I repeat this step, you always understand positive and negative photoresist and bright field and dark field mask. So, if you take a silicon wafer, if you grow silicon dioxide, spin coat positive photoresist, soft bake it as 90 degree centigrade 1 minute hot plate, load the mask, this mask is the bright field mask, expose the wafer using UV light, then unload the mask, develop the photoresist in a photoresist developer, in this case it is a positive photoresist developer, then you post bake it at 120 degree centigrade 1 minute on hot plate. After that, if you dip the wafer in BHF, which is buffer hydrofluoric acid, you will etch the silicon dioxide, and the area which is protected by the positive photoresist is saved. After this, if you dip this wafer in acetone, then your positive photoresist will be stripped off and you will get only silicon dioxide pattern on silicon wafer. This is how you have created a step on silicon wafer, step is of silicon dioxide. This process is called photolithography. You got it. So, this is an introduction to your photolithography technique. In the next class, I will show you how the bright field mask looks like, how the dark field mask looks like, and we will take an example of one single example of a sensor, right, that has a multiple or you can say a chip that will have a multiple sensors indicated onto it. With that, you will have some explanation, some understanding about how the photolithography technique works and what was the reason of learning right from silicon wafer to the oxidation to the lithography and how you can use this chip for a certain application. Alright. So, I will teach till there and as a part of the TA class, right, and then later on we will see some other aspects of the microfabrication as well. Till then, you take care. I will see you in next class. Bye.